is this what you're describing here as well, that there's a kind of a link-up taking place between different computers around the world?
I think that probably these discoveries or making of the net and so on has probably been inspired by attempts to do a similar job on other machines.
Yes.
There's a whole series of machines at CERN for higher and higher energy, but I think that this LHC is probably stressing the the requirements of computing and so on. So,
would this
so
be...
it is made for similar things, the whole net and so.
Yes.
But now one is developing along the ideas of a grid, of this grid, which means that these computers are really collaborating even more than what they usually do.
Yes.
So it is. It's also a great development in computer one is attempting at the same time.
Absolutely. And I mean, it's been about, as far as I read here, 15 years and about $9 billion in the making to develop this whole facility, I think, or if it's only about the LHC, the Large Hadron Collider. Do you think that this is money well spent? Will the experimentation be successful? I mean, considering the research that you're doing now, which seems to kind of say that to the contrary, that it might not be possible now. Then, what's your take on this? Is it money well spent? Is it?
I think it is money well spent, and I would usually come with a remark like that we are one or perhaps more than 1 million rich people in the world, and compared to that, it is not so much.
That's
and
right.
After all, it's an exceedingly fundamental thing to do. I mean, we are looking for something very special in a way, because we are looking for the fundamental laws of physics.
Yes.
One is seriously contemplating that we should make a theory for everything. So one should make a theory that is really valid for everything. This may be objected by some people that this is crazy to talk this way and so on. But I think that the chance is there that we would get out when LHC has run some years, that we might get to a theory that is in principle telling us everything, so that we would be in the stages which a high-energy physicist would say one is in chemistry, for instance. That you know the physics of the atom in chemistry, and it is only the matter of the computer to find out, and you could calculate the properties of any material you want. You can just describe the formula for a molecule, and you can calculate the properties of it if you like, because you have all the theory. So if you could calculate well enough, you could do, and you have great technologies. So even in praxis, you can calculate a lot of things in chemistry. And this is so because you know the theory there. But in high-energy physics, you don't know in principle the theory.
Yes.
Because there are parameters, there are particles, we don't feel safe about whether they exist or not. We don't know really if a Higgs exists or it's replaced by a bound state of something else, like in Technicolor model. We don't know if there's one Higgs or something more like 5 Higgses, like in supersymmetry theory, and so on. And we don't know that there could be new supersymmetric partners, like the superstring theory would suggest. And there are many things we don't know. We don't know whether the couplings may be fine-tuned in some clever way or not, and so on. So there are many questions we don't know. But when we have run with the LHC, then perhaps we would know some of these questions, and maybe we would have a sort of final theory, including even gravity.
Yes. Because I was just going to ask you about that, the question of gravity. Is that something that the LHC could bring us closer to, an answer about that?
Oh, I think so, in principle at least, because I have mentioned the standard model, And this standard model is a very good model, and basically it agrees with all we know so far, except for some neutrino masses and some astronomical things and so on. So there are some troubles, but we have a lot of, there's really no very strong reason that the standard model couldn't work for all we will see at LHC. But this standard model, that is a so-called renormalizable model, and renormalizable means that you can calculate, but there is, in the calculation, you get usually nonsense numbers, but when you do the calculation completely right and relate everything to experimentally observable quantities, instead of putting in mysterious parameters which only occur in the theory but not assigned immediately to the experiment, then you get meaningful numbers. Now, I'm saying here that you get meaningful numbers, but of course you should know that if you calculate naively on models like the standard model, you get not meaningful numbers. Essentially, you only get meaningful numbers when you calculate very, very carefully and relate everything to experimental data. And essentially, the ones who got that got long of the way Nobel Prize for it. So it's not easy to get sensible values out of the standard model, but you do when you do it correctly.
Of course.
But if you add to the standard model, which would be very natural, add the gravity, the forces of the Earth attracting the Sun and so on. If you add this gravity to the standard model, then you get a model that is not even renormalizable. So then you get, in principle, not sensible numbers, even if you relate your things to experiments, if you do it with quantum mechanics and all that. So that means that you get formally meaningless models. But in practice, it is no problem. You can add it without anything. But if you want to be theoretically correct, then when you add this gravity, either you get infinitely many parameters which are a priori nonsense, and then you have to make infinitely many experimental observations to fix it to, or else you are making an approximation. But it is usually very good. So in practice, you have no problem. But for theory, it's very crucial that you should have a better theory for gravity being included together with standard models, so to speak.
Yeah, absolutely. And
that is where string theory can come in, because in string theory you strictly speaking avoid this problem and get meaningful numbers out in principle.
Tell us a little bit more, if you will, about string theory. Are you then the primary physicist behind that idea? How did you come up with this? Tell us a little bit about how that happened, Holger.
Yeah, the string theory that came after the work of Veneziano, who made what we can call Veneziano model or dual model. And he was studying processes where you scatter what we now call hadrons against each other. For instance, when you collide these proton against proton, as in LHC, then you produce a lot of hadrons. That's the most typical one. It's when you produce non-hadrons you get interested, like when you have. But these hadrons, there's one of them is a pion, and he made some formula for how scattering pions against each other and producing another hadron called omega was a nice formula. Actually, it was such a nice formula that it is essentially known as the Euler's beta function. So he had an Euler's beta function description, a very wonderful, simple mathematical expression for the behavior in detail of how these pions scatter in the case when they produce an omega. And that model was very nice and caused a lot of interest. And then I and Susskind and Nambu were those that